In this section, we'll study stability of numerical methods. Earlier in an example, we saw that consistency of numerical method is not enough to guarantee convergence of its solution to the exact solution. Convergence is the key property for numerical methods to have. In order for a consistent numerical scheme to be convergent, a required property is stability. If a scheme is convergent, the scheme will produce a bounded solution whenever the exact solution is bounded. This is the key concept of stability. Let's begin with a definition for grid functions. V is a grid function, and its L2 norm is defined in this way: square sum, and now delta x is multiplied, and whole thing, and power half. Okay, this is a sort of approximation of L2 norm of continuous function. Assume that this grid function is expanded over the domain continuously, then there is L2 norm, and each delta x, the value is evaluated so that there's a kind of trapezoid rule for that integral. So for grid functions, the L2 norm is defined in this way. It's a kind of energy norm. Okay. Now we'll define stability in this definition. Finite difference scheme equals 0 for homogeneous partial differential equations. The scheme is stable if for any positive t, there is constants ct. So this c sub t is depending on capital T, such that, and Vn, each time level, the L2 norm is bounded by the initial, for initial conditions, the energy norm can be found and bounded by this energy norm and multiplied by C sub t. So that means that once initial energy is small, then later energy must be bounded by this quantity. Small, then later on small. That is the definition of stability. Sometimes the initial data is given over multiple time levels. In the case, the stability must be changed into this way. So every possible the input must be considered. So in a sense, it's from 0 to m. There are m plus 1 time levels, and the initial the energy is given, then this is the whole energy. So once the whole energy is given, then later the solutions are bounded by the energy given in the beginning. So this is stability, but we'll use this one mostly because only one level in the beginning, when t equals 0, the initial condition is given. Now, the concept of stability is considered for only homogeneous partial differential equations. The reason is, during the time once a source, the right-hand side f is given, non-zero, the source is given, then the solution energy can increase or decrease. So it is not really the aspect of algorithm. So we want to see the algorithm behavior the stable behavior, so that when we are checking stability, we will consider only homogeneous partial differential equations. It is quite reasonable, the change. In picture delivery, and it's done in this way. In picture delivery, and the people generally follow a sequential process from order placement to deliver completion with a smooth transition and no abrupt change between each step. Along with this strategy, the picture delivery can be more stable. And for this picture delivery, I made a song, Picture Logic and Numerical Methods. You may enjoy this song. It's in rap. Okay. Here we have a theorem. It's well-known theorem, Lax-Richtmeier equivalent theorem. Given a well-posed linear initial value problem and its finite difference approximation, which is consistent. So we will consider this theorem for finite difference scheme and consistent finite scheme. This is true. Stability is a necessary and sufficient condition for convergence. So once it is consistent, then the numerical scheme, if it is stable, then it is convergent. Or if it's convergent, then it is stable. So they are equivalent when the given scheme is consistent. The theorem is very useful and important. Proving convergence is difficult for most problems. However, the checking consistency of a scheme is quite easy. And determining stability is also easier than showing convergence. So that's the reason, rather than proving convergence, people consider stability. Okay, stability is defined in this way. Here, the later energy is bounded by initial energy. But this is also not easy to prove. To show this inequality, and now here we have another theorem, so that once this theorem is satisfied, then we can say that the scheme is stable. Usually a finite difference scheme is defined along with the previous level energy and next level energy, rather than the beginning energy, so that we have to get a theory such that the consecutive time level energies has some relationship. So this is the theorem. A finite difference scheme for a homogeneous PDE is stable if this inequality is satisfied. C is independent of delta t. Now that one is Vn energy norm. This is earlier, just simply the last energy norm, and later energy norm has this relation. Then eventually this will make proof this inequality, that one. So we'll see through the proof. Okay. Recall delta t is capital T over nt for some positive integer. A recursive application of this one, read this inequality. Okay, start with this one. We assume this is true for every n. Then again, for this one, we may consider now 1 plus c delta t and v n minus 2, the grid norm. In this way, we apply this inequality recursively, then we reach at this final term, 1 plus c delta t to the n and v0 and the grid L2 norm. But that is the same as the initial condition. Now here, we have to show that this one is bounded. So once it is a bounded number, then for every level, the energy is bounded by here the constant times the initial energy. So we have to show this one is bounded. Quite easy to do that. Okay, here that one, we can rewrite in this way. Delta t is capital T over n sub t. So we replace delta t with this one and power n. Now, rather than n, we consider the last nt so that we have this inequality. But we rewrite this one in this way. Now we keep this one, nt over ct. Okay, c is a number. We assumed that such a number, non-negative number exists, so that now there's a ct and now over there ct. And at this moment, we assume that c is positive and it's okay. Okay, now look at that one. This is, okay, if we consider this one as x, then that will be 1 over x. Earlier in calculus, you learned that, and here 1 plus x and 1 over x power. As x approaches 0, then we know that this is converging to E. And in fact, this convergence is increasing convergence. Okay? So that this quantity as n becomes nt, becomes larger and larger and larger, and it converges to E, so that now this quantity is bounded by E to the ct. C is constant and t is the final moment of the time, so that this number exists, and here this quantity is a bounded number. So that one is bounded by this quantity, so that eventually we proved the inequality used in the definition of stability. So once for consecutive numerical solutions, this inequality is satisfied, then the algorithm is stable. Okay. Now we consider approaches for proving stability. There are two fundamental approaches for proving stability. One is the von Neumann analysis, along with Fourier technique. But it's simple, but it applies only to linear constant coefficients problems. The energy method is a traditional standard method. It can be used for more general problems with variable coefficients and nonlinear terms. But it is quite complicated, and the proof is also problematic. Depending on the given problem, sometimes way more complicated, sometimes quite reasonably done. Okay, here we'll consider the von Neumann analysis, and it's around it's using a Fourier technique, Fourier transform. Phi is a grid function defined on grid points. Now, so that phi j is the in jth point, then its Fourier transform is given by for every frequency between this symmetric interval, and Fourier transform for frequency psi is defined in this way. This is infinite summation and for the grid points. So right now we assume that and the points are given, and the grid function is given whole real line, and from here there is center, and minus delta x, minus 2 delta x, and delta x everywhere like that. And of course, this one now is defined for the infinite, the interval, but you may think some grid function such that only is non-zero around a finite number of grid points, so that it's not really a restriction, it's a general formulation. Okay. Now, its inverse formula is given in this integral form. You can recover from this Fourier transformed quantities, and from those the frequency, the values, you can recover a given grid point value through this inverse transform. Look at over there. This I is imaginary union, and minus I here, and here that is now positive I, and this is indicating grid point, and this is the frequency. And through the frequency psi, it is integrated over this finite interval and scaled by this quantity, and you can get the grid value. It's well known Fourier transform and its inverse formula. Okay, we can use this mathematics to get the stability analysis. For this Fourier transform, a well-known property is this one, Parseval's identity. Okay, in original physical domain, the energy norm, and this is in frequency domain energy norm, they are the same. And here we already defined it this way. In physical domain, the energy norm is given in this way, and in frequency domain, this is integral over this interval, and this function squared. So it is L2 norm, basically, and only the interval is chosen in this way. These two quantities are the same, so that when we try to prove the stability, now we have to control this quantity. But rather than this one, we may try to control this quantity in frequency domain, because they are the same, and the energy in physical domain and in the frequency domain, they are the same, so that we may consider this rather than that. So we can simplify the computation a lot along with this technique. Okay. So the stability and inequality can be replaced by this inequality. So this initial energy in frequency domain, now that is in nth level, the energy in frequency domain. However, this quantity will be same as in physical domain, also the same. So that rather than original stability inequality, we may try to control to satisfy this inequality. Okay, now let's see this example. And for the Ford-Euler scheme, let's try to show that and it is stable and which condition is satisfied. Okay, the Euler scheme is given when the right side is 0 and given in this way. Now, inverse formula implies that Vjn itself is along with in frequency component and now integral, and you can recover this quantity grid point value. That is the original inversion formula. Now, for each of them, we can get inverse formula, and then now here combine them. Then we have this capital F. Here capital F is, this one comes from this term, and now that is coming from that one, and this term is corresponding to that, and we have such one, and we can simplify in this way. Okay, now so that this quantity must be same as that one, so that is exactly this one. Okay, so we cancel this portion, and V hat n must be same as that one. Okay, so eventually this portion becomes the amplification factor. So for that portion, we are using the notation G theta. Okay, delta x psi. For simplicity, we introduce a theta. So that is G theta is that one. You can see easily. And we can further simplify e to the minus I theta or e to the I theta. And once you expand it, that is cosine theta plus I sine theta. That is cosine theta minus I sine theta. So that we cancel out the imaginary part, and we reach this one. Now further simplify, and eventually we reach that one. Okay, so V hat n, the energy in frequency domain, that is G theta V hat n minus 1. We can apply recursively, and we can reach this quantity, so that G theta is bounded by 1, then the energy is not really expanding. It's independent of the delta t, so that we have to show that we have to find a condition such that G theta is bounded by 1 in modulus. Okay, so here, and that is bounded 1 plus C delta t, but delta t independent, so that eventually we have to show this part. Okay, and here it's not really difficult to show that G theta is bounded by 1, and it's when, if you choose, in fact, if it is too large, then it becomes some negative value. So in modulus, it becomes larger than 1, so that you have to choose mu bounded at half, then it is really bounded by 1. So it becomes the stability condition. And already we know that for the Ford-Euler method, this is the stability condition. And by using the Fourier transform and for Neumann analysis, we reach at the same conclusion, right? We derived the for Neumann analysis and try to prove the Ford-Euler method is now stable when mu is bounded by half, but a little bit complicated. So let's review the technique, the for Neumann analysis. Then it can be much easier to use. First of all, you replace Vjn by g to the n e to the ij theta for every j and n. Now find the condition on the coefficient and grid spacing which is satisfied. Now the magnitude of g is bounded by 1 plus ct. That's it. Now we'll do one more time using this technique, the for Neumann analysis for the Ford-Euler method. Okay. Now we rewrite the scheme, the Ford-Euler scheme, and we replace Vjn with Gn. G is the amplification factor, and e to the ij theta. Then that will be here, and n comes here, and j come here. Now for this one, mu times n minus 1 is power of g, and then now that is j minus 1, so that is e to the I j minus 1 theta. Similarly, you replace other terms. Now we divide both sides by gn minus 1 and e to the ij theta. Then this portion g to the n minus 1 will disappear. 1g will remain in the left-hand side, and e to the ij theta and will disappear, and then this will have 1 minus e to the minus I theta. They will have left over e to the I theta. So that's the result. And left-hand side becomes g, and right side becomes in this way. Again, we are using the Euler formula. E to the I theta is cosine theta plus I sine theta, and e to the minus I theta is cosine theta minus I sine theta. And along with this identity, we can simplify g as this one. But this one is exactly same result as in this equation. So that again, we can get the same conclusion. So for the for Neumann analysis, simply you replace the Vjn by g to the n, e to the ij theta, and then try to find the condition such that the magnitude of g is bounded by 1 plus c delta t. That's it. Quite simple, right? I'm sorry. In computation and systems, stability refers to a system's ability to maintain its desired behavior. Sorry. Despite the small error perturbations. Essentially, stable system will not amplify or magnify these errors, but rather keep them within acceptable bounds. And also, stability in life refers to a state of balance and predictability, and reasonable mood swing, and well thought out decisions. And along with that, we can say in life is stable. So stability used in real life in this way, but in mathematics, the stability is defined so that in each time level, the energy is bounded by the initial given energy. That's the stability. Okay, this is the end of the section. Thank you.